When we first started talking about substitution reactions, we looked at SN2 reactions, and those were relatively straightforward reactions. They were one-step bimolecular in which one um, group, the nucleophile, replaced the leaving group on a molecule. And then we sort of muddied the waters a bit and introduced SN1 chemistry, which led to essentially the same products, but now tertiary alkyl halides can undergo SN1 reactions, and they involve multiple steps. Um, Today, in this video, we're going to muddy the waters even further because carbocations can rearrange. To look at carbocation rearrangement, let's consider the reaction of this bromomethyl cyclopentane with sodium acetate and ethanol. And so the first thing I think we should note is how do we know this is going to undergo an SN1 reaction and not an SN2 reaction? And the big deal that I see here is ethanol. Secondary alkyl halides can undergo both SN1 and SN2 chemistry, but protic solvents like ethanol favor SN1 chemistry, and so this reaction is definitely going to undergo an SN1 type reaction. The next thing we should do is look at our nucleophile. Remember that all sodium salts are soluble, and so sodium acetate is going to split into Na plus and OAC minus. And just to note, OAC is our abbreviation for acetate, and that is the conjugate base of acetic acid. Looks like that. So in this SN1 reaction, the first thing that happens is that bromine or bromide leaves to form a carbocation. And before, we would have said that after bromide leaves, the acetate comes in and attacks this carbocation to form the expected product, methyl acetate and cyclopentane. However, that is not the only product that forms, and it's probably not even the major product that forms. This carbocation can rearrange. And so if we look at this methyl group, there's a hydrogen coming off of that same carbon. And that hydrogen can undergo what's called a hydride shift, where this hydride just shifts over to that carbocation. When that happens, the hydride is over here. And now this carbon used to have 4 bonds. Now it doesn't. That carbon now is a carbocation. Like that. And then from here, acetate could come in and attack this carbocation, which is going to give you a regioisomer of the other product. And in this case, I expect this to be the major product, although this other product is formed. So how do I know that this is going to happen? Carbocations rearrange to form more stable intermediates. So in this example, this secondary carbocation rearranged to form a tertiary carbocation. Tertiary carbocations are more stable, and so this rearrangement is possible. What won't happen is a secondary carbocation rearranging to a primary carbocation or a tertiary carbocation rearranging to a secondary carbocation. The rearrangements only happen if they're going to more stable intermediates. The second type of rearrangement that can occur is a methyl shift. And to look at that, let's examine this reaction of 2-chloro-3,3-dimethylpentane with ethanol. So again, let's look at why we know this is an SN1 reaction and not SN2. The first thing I notice, again, is we have a secondary alkyl halide in this 2-chloro substituent. We have a protic solvent, so that's favoring SN1. We also don't have a strong nucleophile in this case. The nucleophile is going to be our solvent or ethanol, and so that is also pushing towards an SN1 reaction. And so I'm pretty confident that this is going to go through an SN1 reaction. And so the first thing that happens is this chloride leaves to form a carbocation. It's possible, and likely some of this product would form, that ethanol then comes in and attacks that carbocation as we would have expected. We get this oxonium intermediate that another molecule of ethanol is going to come in and deprotonate. To give this expected product that puts an ether in place of the chloride. However, instead of forming that, this methyl group here could undergo a 1,2 shift. And so that methyl group, just like the hydride, shift over a bit to form this. And now this carbon now has 4 bonds. It's happy. This carbon lost a bond. It needs a charge. After that, ethanol can come in and attack the now tertiary carbocation. To form this ether or oxonium ion, which another molecule of ethanol could come in and deprotonate. To give this rearranged product here. I expect the rearranged product that forms the tertiary carbocation to be the major product, but that this product is still formed. If we consider a hydride versus a methyl shift, in general, hydride shifts form faster, and so maybe there's a larger percentage of the unrearranged product in this reaction than there was in the first reaction because this one required a methyl shift and not just a hydride shift. But still, methyl shifts are relatively quick. And so I expect the rearrangement to form a tertiary carbocation to be fast, and this will be the major product. Um, Importantly, groups bigger than a methyl group for our purposes are not going to shift. So we're not going to see an ethyl group or a propyl group shift to do rearrangements. We're going to see hydride shifts and methyl shifts, and one more type of rearrangement that we'll talk about on the next slide. The last type of rearrangement we're going to talk about is a ring expansion. So let's look at this reaction to investigate that. And so again, I've got a secondary alkyl halide that can undergo SN1 or SN2 chemistry. I don't have a strong nucleophile and I'm in a protic solvent, and so those both are going to favor SN1 chemistry. And so I expect this to undergo an SN1 reaction, which means the first thing that happens is this bromide is going to leave. To form this secondary carbocation. After that, we could see methanol attack that secondary carbocation to form this oxonium intermediate, which can be deprotonated by a second methanol. Give this methyl ether product. However, we could undergo a ring expansion, and these can get really confusing. So it's really important to keep track of your carbons when you do this. But remember that cyclobutenes have a significant amount of ring strain. And so we could do a ring expansion to relieve some of the ring strain in this molecule. And so that could shift, and I'm going to number my carbons 1, 2, 3, 4, 5. And so I'm expecting a 5-membered ring now. There's a methyl group here hanging off of one carbon. So that's carbon 1. And carbon 2 lost a bond, and so carbon 2 is going to have a carbocation. And so from here, we could see methanol come in and attack that secondary carbocation. And I'm going to skip some of those steps to form this methyl ether. So that's 2 steps, really, but I didn't show the deprotonation step. Or it gets even more complicated. There is a hydrogen on that carbon. And if this hydrogen were to shift in a 1,2 hydride shift, it would form a tertiary radical carbocation, which could then be attacked by methanol. To form that methyl ether. And so almost certainly all 3 of these products are formed. I expect this to be the major product. Ring expansions from 4 to 5 member rings are fast. There's a lot of ring strain in a 4-member ring. And so this first ring expansion was fast to get to this intermediate. And then remember that hydride shifts are pretty fast too. And so I think that this hydride is going to shift before methanol can come in and attack the secondary carbocation. And so this is the major product. However, these two products are going to be formed in small amounts. There are two different types of ring expansions that we're concerned with. The first one we saw on the previous slide was a 4-membered ring expanding to a 5-membered ring. To give us this intermediate, which then could have undergone another hydride shift to give us the more stable tertiary carbocation. So this ring expansion went from a 4-membered ring to a 5-membered ring, which relieved some ring strain. And then this secondary carbocation rearranged again to give us a tertiary carbocation with a 5-membered ring as the most stable carbocation that we could get to. 5-membered rings can also rearrange, and so this can do a ring expansion. If I number my carbons, my carbocation, I'm going to give 1, 2, 3, 4, 5, 6. And so I'm forming a new bond between carbon 6 and carbon 1. That's going to give me a 6-membered ring. Carbon 1 had a methyl group hanging off of it. And now I have broken a bond with carbon 2 and moved that to carbon 1. And so now carbon 2 is going to have a positive charge. And again, I can undergo a hydride shift to rearrange to form a 6-membered ring with a tertiary carbocation. 6-membered rings do not undergo ring expansion, and this is why. If you were to do this ring expansion, you have 1, 2, 3, 4, 5, 6, 7. That forms a 7-membered ring with a methyl group hanging off of it and a carbocation there. I've got carbon 1, 2, 3, 4, 5, 6, 7. 7-membered rings are less stable than 6-membered rings, and so remember that carbocations only rearrange to form more stable intermediates, and so this rearrangement does not happen. So 6-membered rings cannot expand to 7-membered rings. For reasons beyond the scope of this course, this ring is stable. Cyclopropyl carbocations right here, that is stable, and so 3-membered rings also do not expand. So the thing that you need to remember is that 4-membered rings can expand to 5-membered rings, and 5-membered rings can expand to 6-membered rings, and that's it. No other ring expansions are possible. In a final example for this video, I wanted to compare a methyl shift versus a hydride shift. So again, in this reaction, we have a protic solvent, a secondary carbocation, and a relatively weak nucleophile in CN-. And so I'm going to assume that this is going through an SN1 reaction. And so the first thing that happens is that bromide leaves to form this carbocation. And it's possible that the CN could attack that secondary carbocation to form this product. But likely a carbocation rearrangement is going to happen. And so this methyl group could shift to form this carbocation, the tertiary carbocation, and then CN minus could attack the tertiary carbocation to form this product. But there's a hydrogen here on that carbon, and so that hydrogen could undergo a 1,2 shift to form yet another product. And then that CN minus could attack that tertiary carbocation and give you this product. So all three of those products are possible. Again, I think that this product is going to be formed in relatively low amounts, but I think the rearrangement is faster. And in general, hydride shifts are going to be faster than methyls. And so the major product in this reaction I expect to be this product that arose from the hydride shift. However, all three of these products are formed in some amount. I think that's going to wrap up today's video. We'll pick up with some more practice in class next time.